This is a great problem from a released test. If you could do this problem, you're going to be in really great shape on the AP test. There's sort of 4 separate things going on, but they're all related to this idea of using an integral to describe net change. So watch here. I know there's a beach and there's 2 things going on. This is a pretty common setup for a free response question. So there's the beach and it has sand on it. I know at the beginning there's 2,500 cubic yards of sand before the problem starts. I have 2 forces acting on the sand. I have the tide taking sand away at one rate, which is R. They happen to call it R in this problem. R of t is how fast the sand is leaving the beach. And then, I don't know, there's some kind of big machine, a pumping station they call it, that's like, oh no, the sand's leaving the beach, we better put more sand in, and it's actually adding sand into the beach. So we have 2 things going on. So you might ask, something to think about, which shows me that you're starting to process this problem, is overall, is the beach gaining sand or losing sand? Well, it would depend on which is working faster, the tide taking sand away or the pumping station pumping sand in. And that's one of the things we're going to explore in this problem. So question A. Oh, we know but R and S have cubic yards per hour as their units, and time in this problem is going to be measured in hours. We have 2,500 cubic yards of sand before we start. So question A, this is a nice, slow, easy start to this problem. I hope you find a question like this on the AP test. It should be one of your favorite. How much sand will the tide remove from the beach during the 6-hour period from time t equals 0 to t equals 6? So if you look at that, they're asking about how much sand the tide takes away. It has nothing to do with how much sand gets pumped in. So make sure you don't let letter S influence your answer. It doesn't ask anything about how much sand is on the beach. So however much sand was there when you started doesn't have anything to do with the answer. This is just about how much sand does the tide take away. We know the rate at which the tide takes sand away. They've called that R of t. So rate at which sand leaves, that's the derivative of the amount of sand that's on the beach as a function of time. So I know the derivative of the value I want. So how do I undo a derivative? I'm going to use an integral. So this is a little bit like the problem we just did with the potatoes. So I'm going to write an integral. This is the integral from 0 to 6 of R of t dt. You get 1 point if you write that integral. Don't forget the limits. Don't forget the dt. You could write out the R function, or you could write the function notation for R of t. They would both get full credit. You'll get a 2nd point when you correctly type that into your calculator and report the correct answer, which is 31.815 or 31.816 cubic yards, depending on whether you round or truncate. So, and then let's talk about why we know those units, yards cubed. R of t is measured in cubic yards, that's yards cubed per hour, and an integral models adding up a bunch of small products. So in this case, my product is the R of t value times the tiny change in time, dt. We've been told t is measured in hours. So every one, if you can imagine, if I was going to make rectangles, either to approximate or, so you can imagine I was drawing rectangles, either infinitely many rectangles or I was just approximating rectangles. The height of every rectangle would be measured in cubic yards per hour, and the width of every rectangle will be measured in hours. So when I multiply cubic yards per hour times hours, the hours will cancel, and I'm left with units of cubic yards. So 31.815 cubic yards. All right, the whole rest of your success with the rest of this problem depends on your ability to do letter B. And letter B, it's an example, it's an application of the most important example in chapter 5. I've been asked to write an expression, y of t, for the total number of cubic yards of sand on the beach at time t. And I've been very specific, I'm supposed to call it y of t, so I'm going to start by writing y of t. Now to think, what do we know about y of t? Well, we know one ordered pair. I'm going to write it down here. I know that when time is 0, how much sand is on the beach? 2,500 cubic yards. I know that has to be an ordered pair on my function. And I actually know about the derivative. So what's happening here, I know that R of t tells me how fast sand leaves. So that's sand I want to subtract away from the beach. And we saw that to find that amount of sand, I would have to integrate R, because R is a derivative. It's a rate of change of the amount of sand. And I know the rate at which sand comes in, so I'm adding to the amount of sand on beach. That's adding in the integral of S. And that tells me about my derivative. So I can write that expression. I'm going to integrate from 0 to t. The amount of sand coming in is S. I can't use t because I've already used it. I'm going to use S of p dp minus the integral from 0 to t, that's a t, of R of p dp. Imagine taking the integral of that equation the way I have it written so far. It's not finished, but imagine taking the integral and the imagine taking the derivative. Imagine finding y prime. The derivative is going to cancel out the integraling and give me capital S of t minus capital R of t. That's the derivative. The rate at which the amount of sand is changing, it's the rate at which sand is coming in minus the rate at which sand is going out. So then notice the only thing I have to fix about this, it can't be my y of t, because I still need to make it so that when I use 0 for t, I get 2,500 as the result. So this is one way to write your function y of t, 2,500 plus the integral from 0 to t of S of p dp minus the integral from 0 to t of R of p dp. Notice you would get just as much credit as just as good an answer if you made that one integral. So I'll write it just so you can see what it looks like. This is another good answer, the integral from 0 to t of S of p minus R of p, but notice that needs parentheses or brackets to get its dp. That's another great answer. Okay, so I left my answer there because it's going to help us on this next problem. Letter C asks, find the rate at which the total amount of sand on the beach is changing at time t equals 4. Well, what was the y function we wrote? That's the amount of sand on the beach. The rate at which the amount of sand is changing, therefore, would have to be y prime. So the thing I'm looking for is y prime of 4. I'm going to write that down here. Of course, I can't tell what y prime of 4 is until I've written an expression for y prime. So let me do that now. Although if you caught most of the discussion in that last part, you could probably do this more quickly. Feel free to do this more quickly. But since I have y written, I may as well use it to help me find y prime. So y prime of t, the derivative of 2,500, is 0. Plus, I'm going to take the derivative with respect to t of the integral from 0 to t of S of p dp, that's S of t, minus the derivative of the integral from 0 to t of r is R of t. So there we go. That's not so bad. That's the big connection they want you to make in this problem, is the rate at which the amount of sand is changing. It's the amount of sand coming in minus the amount of sand going out. And I can use that relationship. I can use those two rates plus that initial condition, 2,500 cubic yards at the beginning of the problem, to write an expression, write a function that can give me the amount of sand on the beach at any time t. So now that I know y prime of t, y prime of 4 is going to be S of 4 minus R of 4. You would use your calculator. Notice this is a calculator active problem, which gives you negative 1.908. So there's two answers published in the answer guide, so it depends whether you truncate or you round. To clarify, that's a negative 1.908 or negative 1.909. And then think about the units. Y of t was the amount of sand on the beach measured in cubic yards. So the rate of change of y is going to be cubic yards per time unit, in this case cubic yards per hour. So y prime of 4, negative 1.908, or negative 1.909 cubic yards per hour. Okay, so this is an important one, this part D. It's an important one to see the video on because there's not really a good place in your book to show you example problems. Your best examples are going to come from that free response notebook that you have. Check this out. For time between 0 and 6 hours, at what time t is the amount of sand on the beach at a minimum? Wait a minute. Minimum is a superlative, and I know that when I hear a superlative, I'm supposed to think of optimization. So conveniently, I've attached your chapter 4.4 notes to this video if you want to get it, if you're using TouchCast. So we have to remember everything we knew about optimization. And you fought me back in chapter 4, but it's coming back. It turns out these ones are a little bit easier. You won't usually have to draw a picture. Okay, remember, an optimization problem is just a big fancy way to get you to find the absolute maximum of a function. And we have to remember that, or maximum or minimum, an extrema, an absolute extremum of a function. Those can occur at the locations of relative extrema, so local mins and local maxes, places where the first derivative changes sign, or they could occur at endpoints. So we had two kinds of points we had to add to our t-chart: the endpoints of the interval, and then any local minimum or local maximum. Any critical points is where those happen. So places where the first derivative of whatever quantity you were trying to optimize was equal to 0. So come back to this problem here. Oops, this problem here. At what time t is the amount of sand on the beach at a minimum? So I'm going to make what I know. The amount of sand on the beach. I already have an expression for the amount of sand on the beach. I called it y of t. So let's just remember the things that I know. The inputs to the function, the inputs to the y function, the quantity I care about, are times. So I have two columns. I'm going to have a time column and an output column. In this case, an amount of sand on the beach column. And what important values go in that time column? The endpoints, which are 0 and 6. And this is the part you have to remember. What else goes in that t column? It's going to be critical points of y. Now here, specifically, we're looking for a minimum amount of sand, which means that we could limit our search if we wanted to relative minimums, or we could just put all the critical points in here. Since it's a calculator problem, you usually don't spend too much extra time if you put them all in. So how do I find critical points of y? Well, I need y prime to equal 0. If you want credit on the AP test, you would get 1 point if you could write that expression, that equation, y prime of t equals 0. And you'll get a second point when you solve it. So on your calculator, let's see if I can do this. Well, just a brief overview. You can see what I've done here, and then you can try it out when you get to class. I highly recommend you actually go through the motions on this problem with the calculator in front of you. So I wrote y prime, which I figured out in part C was s of t minus r of t. So I had to type out s of t minus r of t, and I'm graphing it. And I get this. I changed the window to go from time 0 to time 6 because those are the only times I care about in this problem. And you can see that there is a place where there is a time value for which s of t minus r of t equals 0, and it happens right there. So I use my calculator function. That's the 0 function, so second and calc and 0. And I remember I have to give a point, I have to move the spider a little bit to the left, and then move the spider a little bit to the right, and I come up with my last critical point, which is at a equals 5.117.865. Sorry, I started writing it too close to the middle of my t-chart. Okay, so now that I have that missing point, Here's the real picture. I had neglected to notice that my calculator was set to degrees. Now that it's set to radians, you can see the actual solution to y prime of t equals 0, which is 5.117865. Okay, so now I have a t-chart full of candidate values, and all I have to do is use these t values in my y function, which I wrote back in part 2. I'm going to get, well, I already know this guy. When time is 0, there are 2,500 cubic yards. I'm going to use 5.117 as t in the y function. I'm going to use 6 as the t in the y function, and I'm going to come back and pick the one that gives me the biggest output. So when I use 5.117865, my y turns out to be 2492.369. You should give all of these answers to 3 decimal places. When I use times 6, I get 2493.2766. So I can see that the smallest y value I get happens at that time 5.117865. So I'm going to go back to the full screen, and I'm going to type up how I would type my answer to this problem. Okay, so note this first part of my answer. I have to say why I only have to check those 3 time values. So I would say candidates for the time at which the amount of sand on the beach is a minimum are times 0 and 6, because they're the endpoints of the interval, and solutions of y prime of t equals 0. That's another way of saying critical points of y. That would be another way to say this, but you definitely, to get credit, are going to need either to have written that equation, y prime of t equals 0, somewhere. Remember, that's the equation we solved on our calculator using the graph, and you can't get credit for solving an equation on your calculator if you haven't written the equation. So we have written y prime of t equals 0. Okay, so now the next step in my decision, don't worry, it's the last step, is I look through all the y values at the important t values, and I can conclude that the smallest one is 2,492.369, whatever it was. So watch how I write up the rest of my answer. So now I can answer their final question. They asked me at what time is the amount of sand a minimum, and what is that minimum value. So in this case, they're asking for both the input and the output to the y function at that minimum. Sometimes they only ask for one or the other. So I would say the minimum amount of sand is 2,492.369 cubic yards. Notice that has to be given to at least 3 decimal points. To 3 decimal places, at time t equals 5.117 hours. Make sure you're giving units. Notice 5.117, I could have rounded instead and given 5.118. That would get just as much credit.